started looking at the few examples after solving certain problems. After solving for the element formulation, the first problem was the point load and a bending moment such that we discretized it into two elements. The next thing we did was we took the problem in which there is a roller here, there is a fixed end here, and there is a point load at this place. So for solving these same problems, these two problems, what we have done is we discretize each member into two elements, element 1 and element 2. Even in this case, element 1 and element 2, and then we applied our load and moment at this place, and here in this case we applied this. We know the stiffness matrix standardly obtained from that EI by EL cube 12 6L. So you look into the older stuff. So this which we have developed, and based on that we assemble the global stiffness matrix, we assemble the global force vector, and then we condensed it by applying the kinematic boundary conditions. Once the kinematic boundary conditions are applied and KUU is condensed, the KUU is in a shape is invertible, and using that what we did is we tried to obtain the unknown degrees of freedom. Once you know the unknown degrees of freedom, using the second part of the condensation, what we did is we found out the reaction forces. That is one class of the problem. Then the third, which we will be also doing it today, the third one is uniformly distributed load. So let us solve the same problem again today. So let us take a cantilever beam and apply some W. This is of length L and flexural rigidity is EI, where we'll take W is equals to, and L is equals to 100 inches, E 30, and I is equals to 100 inch for. Next, let us solve this problem analytically first. So what I will do is I will try to get an analytical solution. Second, we obtain one element FE solution, and then if possible we'll do two element FE formulation. So let's continue in the same manner. So there is a lot of confusion in the students with respect to the sign conventions. So let me write the sign conventions. So if I take a beam, these sagging are positive bending moment, and hogging would be negative. The shear force would be something which is positive, and vice versa. This is the sign convention for the bending moment and shear force. Okay, let us take this cantilever beam, which has uniformly distributed load where W is a constant. That is the problem we are solving. So at a distance x, x is measured from here, total length is L with a flexural rigidity EI. We know that EI d square y by dx square is equals to m. So m at a section x. So m of x in our case the reaction forces from this W into L and this moment would be W L square by 12. Okay, so under the distributed load, so moment at a section S would be L square by 12 plus x. So our analytical solution can be obtained by solving this expression. Okay, since this is an explicit, we can directly integrate it. By on integrating it, we will get further on integrating one more time. But we have the boundary conditions of for the current problem as y of 0 is equals to 0 and dy by dx of 0 is also equals to 0, because our left hand, since this is fixed support, the displacement and the slope of 0. So that's the things which we have written it. On substituting on these two things, we can clearly show that this will yield C2 is equals to 0. Okay, next in this if we substitute, it will clearly give that C1 is equals to 0. So fortunately our both the constants of integration turned out to be 0, so our final expression for the elastic curve is given by so this is our expression for the elastic curve. Now, if I want to know the deflection and the slope at the point B, that is where x is equals to L, then so this will give us our deflection at point B. So similarly, if you use the expression for the dy by dx, and we substitute at our elastic profile also is there. Now let us have some, let us see the characteristics of the um, of exact solution. The characteristics of exact solution is, if you look at this, this is our okay. I will try to rederive it. I have just made a mistake. So let us rederive the solution. So I have made a mistake. Let me restart it. So let us start with this problem again. So we have the bending moment went wrong somewhere here. The bending moment was incomplete. So we have to repeat all these things. So we have taken the contribution of this one, and there is a uniformly distributed load, which I forgot to add into the picture. So the next contribution is Wx, into x by 2. This is the contribution of the total bending moment. I'm sorry about that. I made a mistake. Because of that, our entire exercise went wrong. So this is our bending moment, expression for the bending moment. If this is the expression for the bending moment, EI d square y by dx2 is equals to minus WL square by 12 plus WLX minus WX square by 2. And if I integrate once, it will become EI dy by dx is equals to minus WL square by 12 x cubed by 6 plus C1. Similarly, if I integrate it once more, right, then apply my boundary conditions. My boundary conditions are given by at x is equals to 0, y is equals to 0, and dy by dx is also equals to 0, because the left end is a fixed support. So based on that, one can conclude that this implies C1 is equals to 0, sorry, C2 equals to 0, and this implies C1 equals to 0, and hence the elastic profile EY y of x is equals to minus W L square by 24 x square plus WL x cube by 6 minus W x4 by and that can be simplified as W by 24 minus L square x square plus L x cube times 4 times L x cube minus x to the power of 4 is the given EI times the displacement elastic curve, and EI times dy by dx would be W by 24 into minus 12 minus 4x cube, that is equals to W by 12 minus L square x plus 6 L x square minus 2x square x cube. So if you look at this solution, this is your exact solution. So this is the exact solution for the if you look at it, the expression of y of x is a fourth order polynomial. So that is the characteristics. Exact solution is a fourth degree polynomial. Similarly, exact solution of theta of x is a third degree polynomial. So this is the characteristics. Now we will try to establish what is the value of y at b. The displacement and slope at the free end. So to find out that, what we'll do is we'll take y and evaluate at L. So y at B is obtained by 1 over EI times W by 24 L4 into minus and minus 1. This equals to W L4 by 12 EI. Let me just check if I have made any mistakes this time around. So minus L square x square plus 4LX cube. Hopefully this is correct. And similarly, one over EI W L cube by 12 this would be minus 1 plus 6 minus 1, that makes it 4 W L cube by this is, so this is your yp and this is your theta p. So now we have obtained our exact solution and also evaluate the displacement and slope at the free end, which is the free end, that is x is equals to L, right? So from the our analytical expression. Now since we have obtained the full solution in the exact manner, this solution we can use to compare our results when we obtain the similar solution or the solution or what we call it as approximation from the finite element things. So we'll obtain the firstly obtain the approximation from the finite element like we have done in the previous class, and then compare it values with respect to the to this given value. Okay. So again, let's take this problem. The second, the B case is one element F is solution. So the one element FE solution is for the problem is as follows. So you take this, now we model this one or we mesh it using only one element, which is, let's say, node 1, node 2, and this is element 1. And for this, the degrees of freedom would be d1 and theta 1, d2 and theta 2. So based on this, and what we have done is the equivalent or the consistent loading in the previous case. The consistent loading says that our, let us see the consistent loading once more because there was sign convention wrong in the previous class. So let us take a fixed beam. It's with a uniformly distributed load. Somehow we know the exact solution or the reaction forces for this problem is this would be my force at this place, positive force, positive M, positive. So further, so when I come to this is loading 1, case 1. This is the case 2. The case 1 has this reaction force, and this is case 2. Case 2 is I have WL by 2 in the downward, WL by 2 downward, a movement here in the clockwise direction, movement here in the anti-clockwise direction. These two things will still have the same reaction forces. Because of that, these two are called as equivalent. If these two are equivalent, I can statically equivalent because their reaction forces are same. So whenever I see these kind of a loading, I substitute this set of loading conditions. So for this set of loading conditions, let us write my force vector as, now this, look at the direction of this compared to this one. It is in the opposite direction to with respect to this thing. So that's the reason I put W with whatever is the magnitude. This direction is the positive direction, whereas the moment at this is in the opposite direction. So I again put a negative sign. Now this one is in the positive direction, but this one is in the opposite to that. And this one is positive direction. This one is also positive loading vector. How I have to take care of it. Now with this, as my loading condition. So let us solve the one element solution. So for the one element with EI and L, we know the stiffness matrix is given by is our stiffness matrix. Our degrees of freedoms are, let us see the degrees of freedom. The this is capital D3, this is capital D4. So our degrees of freedoms are with respect to D1, D2, D3, D4, D1, D3, D4. So in this problem alone, our entire structure is made up of one single element. Hence our K global in this case alone is same as K for this problem. And hence, so my K global now this is same D1, D2, D3, D4. Now, since we have obtained this set of solution, then I have to apply my boundary conditions. Sorry, before that I need to find out my force vector. To find out the force vector, my F global is same as F1, F element 1, and hence so which is nothing but now this is the applied loading. So our beam, which was is made equivalent to a beam with WL by 2, WL by 2, and which I make it as further equivalent. I'm not considering these two things here because they are already applied on the support. So your reaction forces obtained from this has to be incremented by the same equal and opposite values. So that's the reason I will only solve for the problem, which is nothing but W by 2 and W square by. So that means my F global I would be solving for is 0, 0 minus WL by 2 and WL square by 12. And then I apply my knowns. Knowns are D knowns are D1 and D2 because D1 is equals to 0, theta 1 is equals to 0, which is nothing but capital D1, capital D2. So my KUU would boil down to by striking off the D1, D2, D1, D2, I end up with my KUU. Yeah, well, you're missing. So now KUU, so these are the knowns, and DU unknowns are D3, D4. So DU is equals to FU. So my FU in this case is nothing but minus WL by 2 and WL square by 12. So if I use this, my D2 2, which is nothing but D3, D4 are also known as D unknowns is nothing but AUU inverse inverse WL by 2. So let us try to find the solution of this. TL. equals to inverse of AUU. That turns out to be here when I'm solving the problem, I considered this guy as A. So that is the thing. So one by 3, 1 by 2L by 2L, and 1 over L square into minus WL2 and WL square by 12. Let us try to solve this thing. So when you multiply this will be L cube by AI to, we can even take, okay, let's just keep it W. L is taken common, so times minus 1 by 6 plus 1 by 24, and this one is, we'll take WL square common, so this will be, WL should be uh, that is L cube by 3 AI. Okay, just I might have made, so let us just compare. This one is 3 into 6 minus 1 by 6. This one is LL get cancelled. LWL is already taken care of, 1 by 24. So since I've already taken WL square common, so WL, so if I take W common, then 1 by 2 minus 1 by 4, and this is uh, perfect. So this will be like 4, 1 by 8. And this one is 3, 2. So Let me just check once again about my math. WL by 2, WL by 2, 1 over 6 is 24, into 3 into 6 minus 1 by 6. This is 1 by 4, 12. So this is 4, 3. Let me just see if I have. Because I think I made it quickly for the correctness. So let's redo it for the one last time. So the analytical solution is ei e square y by dx square is equals to m of x, and m of x for this problem is W into L is the reaction force, and WL into L by 2 is the moment. So I think I'm out of my mind today. So anyway, if I have to take a section at this distance, so what I will have is minus WL square by 2 plus WL into x into WX into x by 2. So let me just see here once more. So since I have a small thing whose load is Wx reacting at a distance of x by 2, this is correct about it is causing a kind of clockwise, so it is with a negative sign. WL square by 2, everything is fine. So dx square ei is equals to minus WL square by 2 plus WLX minus Wx square by 2. If I integrate it, dy by dx ei is equals to minus WL square by 2 x plus WL square by 2 Wx cube by 6 C1 y is equals to W square x by x cube by 6 minus W x to the power of 4 by the boundary conditions are at x is equals to 0, y is equals to 0, dy by dx is equals to 0, implies my C2 is equals to 0 and C1 is equals to 0. So my y of x is equals to 1 by ei w by ei minus L square x by 4 plus Lx cube by 6 minus x to the power of 4 by 24, which can be written as w by 24 ei minus 6 L square x plus 4 Lx cube minus x to the power of 4. Now similarly dy by dx at x is equals to w by 24 pi into minus 6 L square x plus 12 L x square minus 4 x cube, which is nothing but w by 12 pi minus 3 L square x plus 6 Lx square minus 2 x cube. Now if I evaluate at x is L, minus 6 4 minus 1, this turns out to be minus 3, that is w 4 by, which is same as the other one. So anyway, and dy by dx at x is equals to L is equals to w L cubed by 12 ei into minus 3 6 minus 2. This will be 1 by 12. Still I haven't got the things right. So I think I have let me just correct myself. So this expression for the displacement minus L minus L square x square by 4 W plus Lx cube minus this statement is correct. So when I try to differentiate, when I simplify it, it comes out to be the same thing. So this is fine. from here when I make it. Okay, so today's class is full of mistakes. This is 12. This is also 12. 4 into 3, that makes it 12. And so that would be fine. So this is again wrong, so let me erase it. For anyway, I'll just give this expression is correct, which I've checked. So this expression is correct. So this is my exact solution, and on evaluating we should also get our dy by dx would be same as wl square by. So these two are correct. So this has to be coming out to be. We'll check the math later. So let's not kind of wait the class with my mistakes today. This should come out to be something like 6ei. So let me just for once I will quickly check my solution, and then we'll kind of proceed it. So w by ei minus l square x by 2 plus x cubed by 2 minus x 3 by 6. So this would be this expression. W by ei minus L square x by 2 plus Lx square by 3 minus x cube by 6, that is equals to W by 6 EI. The expression. So if that is the expression, so then this would boil down to 6, 3. So 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 what we got from the analytical solution is YB is equals to minus WL4 by 8EI, and theta B is equals to minus WL cube by 6EI. So if you look at it, your FE solution will also have the same thing, sign. So the displacement, so the entire exercise is to show that at nodes the FE expression or FE solution will exactly match with exact solution. This has to be true. This has to be true for all the degrees of freedom. Now let us also try to get the shear force and bending moment given the expression from the analytical things. So let us take again, this is my dy by dx. So let me rewrite it. Exact solution y is equals to w by 24 ei minus 6 l square x square plus 4 lx cube minus x to the power of 4, and dy by dx is equals to x square minus x cube. If I take ei d square y by dx square should be the m, that is equals to w by 6 into minus 3 l square plus 6 lx minus 3x square. Similarly, v is equals to ei d cube y by dx cube is equals to x to x. This is our bending moment and shear force coming from the exact solution. However, if you look at our FE solution, the FE solution is given by this. So YB theta B is this one. So let's come back to the nodal solutions. So one element FE solution. So our D1 is equals to 0, theta 1 is equals to 0, D2 is equals to nothing but YB, that is equals to time WL4 by 8EI, theta 2 is equals to theta B, that is equals to minus W L cube by 6EI. Now our approximation says that Y tilde is equals to DI NI. So that is equals to D1 N1 plus D2 N2 plus D3 N3 plus D4 N4. If you go back to the previous classes, we have shown that N1 of X is equals to to 1 by L cube 2x cube minus 3x square L plus L cube N2 of X is equals to cube minus L x square x into L square N3 of X equals to 1 over L cube into minus plus 3x square L and one thing we can observe from all these things is each one of it is a third degree polynomial. So if this is third degree polynomial, if you multiply some constant values like D1, D2, D3 and D4 and sum it over, then your Y tilde is also third degree polynomial. Anyway, in our case, D1 is equals to 0, D2 is equals to 0, D3, this is our D1, this is our D2, this is our D3, this is our D4. So we can write our expression as Y tilde is equals to D3 N3 plus D4 N4, which is nothing but minus W L4 by EI into 1 by L cube to minus 2x cube plus 3x square L minus W L cube by, this is 8EI, this is 6EI, 1 over L square x cube minus Lx square is your approximation. So you can simplify it, but you can see that this is the third degree polynomial entirely, but whereas y exact is fourth degree polynomial. Let us have a look again. So the exact solution, the feature of this FE is at the nodes our equilibrium is enforced. That's the reason the nodal solutions would match. That means at the nodes you should get an exact solution, while in between the nodes it is not guaranteed the solution is exact, because the solution in between the nodes is purely an approximation. In this case it happened to be a third degree polynomial approximation, when the exact solution happens to be a fourth degree. So this is the reason which we have written earlier. The characteristics of exact solution is it's a fourth degree polynomial. However, here the approximation is only third degree polynomial. So your FE solution will not exactly match with your uh, with your uh, exact solution. But how to make sure that our FE solution will try to give a uh, closer to exact solution? That those things are achieved by saying that if you increase more number of elements, let's say instead of one element solution we go ahead and seek for two element solutions, then or four element solutions. So that means we are fitting a piecewise third degree polynomial over over the regime. What happens, this piecewise solution will have a closer approach. And d square y by dx square ei with a tilde. This is not m of x, it is m of x obtained through the approximation y tilde, which we call it as m tilde, is obtained by it's already 12. So this is 12 ei into uh, and sorry, the EI is gone since I have already multiplied with respect to EI. This has to be gone, and V tilde of x is equals to EI V cube y tilde by dx cube is equals to minus WL by 12 into minus 6. So if you have seen, V tilde of x is a constant, M tilde of is linear. Since we are differentiating, it would be like this. This is quadratic, this is cubic. So now let me kind of summarize it. Here our solution would exactly match at the nodes. The solution means our degrees of freedom. However, the m of x and v of x, when we evaluate at L, one has to be shown it here. M of L is not equals to M of L, and V tilde of L is not equals to V of L. However, Y tilde of L is equals to Y of L. It has to be, and theta tilde of L has to be theta of L. Okay, so this I will do it again next time, and then I will show you something with respect to inclined beams, and then I will show a MATLAB program, complete program, how to solve an inclined frame which has both bar, beam, and some elastic foundation. That will kind of give a summary of the entire chapter 3. So maybe in one class I will like to finish it. So this this has, because this is degrees of freedom, it has to satisfy. These are not degrees of freedom. M and V are not degrees of freedom. It's something like kind of conjugates of these things. So these things only match at the midpoint, which I will draw it in the next class since we are running out of time. So to summarize, what we have done is we have solved this problem with one element and shown that FE solution is not same as exact solution. FE is an approximation. However, FE solution matches with your exact solution only at the nodes. So if you have more nodes, that means with H convergence, that is with more and more elements, the piecewise solution will be closely looking to the exact solution. However, the kind of forces or the stresses are not exact at the degree of freedom. At a later point in the chapter 4, I will show that the stresses are exact at something called as Gauss points, which I haven't introduced at this given point of time. So what we'll do, we'll end this class, and because of some network issues and my bad math today, we had a lot of errors, silly mistakes in the things. I hope you have clarity in what we are deriving. If you have some questions because of some typographical errors I made today, please write back to me. I will try to go through it and explain it in detail in the next class without these errors. So if you have any questions, please ask.